Good morning or afternoon. My name is Eric Appelman. I'm a Dutch national. I'm 57 years old, chemical engineer, and I have a very diverse career behind me in various multinational companies. I'm not going to bore you with all these details, but I do want to mention the last one. That is my current employer. That is the Brightlands campus, which is in the far south of the Netherlands. Let me say something about this Brightlands campus. It is an initiative of the regional government of our province, which is called Limburg, the Regional University of Maastricht, and company DSM. And it aims to offer a home for companies and institutes that are working on the chemical industry of the future. We are looking at processes, we are looking at materials, and we are also looking at biomedical solutions. Okay, back to the topic of today, and this is about sustainable heat for the chemical industry. We shall not lie about this. The chemical industry is a large contributor to greenhouse gas emissions, and we have a high obligation to keep our planet livable for ourselves and our children and reduce those. And most of the emissions in this industry are from the production of energy. Some of that energy we cannot recover. For the chemists among us, we know that some of the heat is stored into different molecules, and you cannot cover that back. But a lot of everything that we use in terms of energy is to heat up molecules to the temperature that the reactions will happen, and after the reaction is over, we have to cool them back because we want to use them cool. That has to be removed, and a lot of the chemical industry has made it a high art to do that recovery process with very high efficiency. But of course, there is always something that is lost. What is a little bit more complicated is that we typically have to add the energy at very high temperatures. Temperatures as high as 1,000 degrees. And then you can recover, but you will never get that at 1,000 degrees. You will get it available at lower temperature. So if you do recover your energy, it always comes at a loss in terms of the quality of that heat. Electrification of high temperature processes is one way to not only eliminate the emissions of carbon dioxide, but also to deliver heat with a very high quality, because it is relatively easy to harness electricity to produce very high temperatures indeed. The challenge is actually even more pressing because the processes that do happen at these very high temperatures, processes like steam cracking and steam methane reforming, catalytic reforming, production of cement, production of iron, are among the largest in the industry. And I don't think I'm lying if I'm saying that more than half of the energy that is used in the chemical industry is for those very high temperature processes where electricity is the solution. There are a couple of technologies, and they have never been used because it was always cheap and effective to burn gas or something else. But there are a variety of electrical techniques. There is plasma technology, shockwave technology, there is various resistive heating technologies. We can do it with infrared radiation. There's even electrochemical technologies. All of those, and that's the interesting thing, are investigated and scaled up at the Brightlands campus in the Netherlands, and I'm very proud to share that with you. One area that I really like and that I'm really proud of is plasma heating. This is an old technology. We have not invented it today. It's actually already 100 years old. What you do is you let electricity go to gas, which becomes ionized, and you have temperatures that are well in excess of 1500 degrees C. And not only do you deliver then the heat at this very high temperature, you only enter an area where conventional heating technologies cannot come at all. So you can have altogether new chemistries. Examples, the conversion of methane to directly C2. Some of you may know how we've been struggling to do processes like oxidative coupling of methane to go from C1 to C2 chemistry. Well, this process does that relatively easy. It also produces a lot of hydrogen on the way. Another one, a bit of a holy grail, is the conversion of carbon dioxide to carbon monoxide, where we also have a few adjacent challenges. What is interesting about this technology, that it is surprisingly relatively low in capex, and it can be rapidly turned on and off, which is not common for high-temperature processes. The revitalization of this process, which was invented more than 100 years ago, which had its heyday probably 50 plus years ago, and now is looking towards a new future, has been picked up by the University of Maastricht at its circular engineering department here on our campus by Professor Van Rooij, of whom I have a picture here. What is also very interesting is that as soon as this group started, and it is growing quite rapidly, I have to say, you see that a variety of small, often startup companies start to flock around. And we have now a real center of expertise in the build-up around plasma conversions. Another spectacular technology is Shockwave. In this case, we use an electric impeller or something similar to accelerate a gas to speeds in excess of those of sound in that gas. And what happens is that if you suddenly decelerate that stream, for instance by widening the tube, the same thing happens as in a big traffic jam. The cars that come from the back have nowhere to go because they are operating in excess of the speed of light, of sound. And what then happens is that instantaneously you get homogeneous heating to extremely high temperatures. Those conditions, those high temperatures, are perfect for instance, steam cracking, because not only you got the very high temperatures that we want there, but also the very short residence times that are desirable for these processes to make sure you don't get any consequential reactions. The company that is at our campus is a pioneer in this field, and it is called Coolbrook, and it's from Finland. They have designed the machine that you see there on the picture, which basically could be not much bigger than like 5 meters long and 2 meters wide, and do tens of thousands of tons of cracking per year, for which we today need very, very large furnaces. So not only will you have an electrified option that doesn't emit CO2 from burning leftover gases, it is also very compact and it is very flexible. On a related track, the campus, the Brightlands Camelot campus, also facilitates a similar track pursued by some of the largest petrochemical companies in Europe, together with leading technology providers Technips and Siemens Energy, where we are pursuing a very similar thing. So you could almost say that in the field of very high temperature processes, powered by Shockwave technology, we have a bit of a center of excellence. On the more traditional field, you have resistive-radiative heating technologies. And here I actually do not have very good pictures, but as a matter of fact, we do this at home every day. Our deep fryer at home, where you do fry your chicken or your French fries or whatever else, is an example of a resistively heated installation. Current goes to a conductive material, the material gets hot, the hot material heats up whatever is around, in this case frying oil. Conventional temperatures for familiar reactions, but it could actually be quite high. You can also go to temperatures as high as 1000 degrees C. And there are today companies and institutes that are pursuing this technology, for instance, again, for the process of steam cracking at 1000 degrees. An alternative is what we sometimes call indirective resistive heating. That is what happens when you're sitting on a cold terrace or a cold patio in the winter. There, the same current goes to the same conductor and it is hot, but rather than heating directly the air around it, it radiates, and the radiation comes, for instance, on your body, and then the body is heated instead of the air around it. And also that technology can be applied and is actually applied on large industrial scale. Today, probably a little bit more in temperature in processes where we would like to keep a temperature than where we would like to heat it up very much so, but there's actually no reason to not do it. Also, these two technologies are pursued at our campus by various companies, often in the startup field. So, if I can summarize for that, if we would really like to decarbonize our chemical industry, we have to tackle the challenge of doing very high temperature reactions through electricity rather than through classic means like burning gases and having flames. The good news is that the electrification is very suitable to achieve those high temperatures, actually more easy than the gas flame. But the transformation is not trivial at all, and we have to do substantial scale-up work. Another one, but that is a bit outside our control, is assuring the continuous availability of electricity, and the renewable electricity in particular. And we know how to make them, but to have it available 24/7 and 365 days per year, that is a bit of a challenge. I do not know the precise answer, but what I do know that at our Brightlands Camelot campus, we have all key technologies that will help us to do very high temperatures through electrical heating methodology available, and that they are scaled up. I would like to invite you, actually, if you are interested to learn more about it, to contact us. And if you do have another technology, or if you do want to scale something up, or if you want to do anything else which has to do with the chemical industry of the future, you are cordially invited. Thank you for your kind attention.